All right, good afternoon, everybody. As Lena said, my name is Doug Litteken, and I'm an engineer in the Structural Engineering Division, which is right next door here in Building 13. I started at JSC about 5 years ago, and back then it was a very exciting time. The space shuttle program was ending, and we had a bright-eyed future going back to the moon and onto Mars. And I started looking around, and I saw a lot of cool projects. I saw lunar landers, lunar rovers, some cool habitats. But there was something that I saw common in all of these things that kind of concerned me. Everything was the same. Everything was the same as it always had been. Nothing really seemed to change. Everyone was still building things out of metal. And yeah, I'm talking about aluminum and steel and titanium and metallic structures. And I know that the space program has been built on metallic structures. But we're trying to go beyond low Earth orbit. We're trying to go to places we've never been before. In order to do that, we have to do things that we've never been before. And so we need to do some other things. So I started to steer my career away from metals. I started looking at composites and fabric structures. And these are the things that we need to do. We need to innovate. We need to change. We need to get out of our comfort zone and try new things. So we need to try some things like inflatables. And so what is an inflatable structure? This beach ball, for example, is an inflatable structure. You've seen this before. You've seen a lot of other things similar to this, like rafts, air mattresses, party balloons. These are all considered inflatable structures. In essence, they're a mass of material, and then they get inflated, and they grow into a larger volume, and they occupy the space that they've been designed for. This beach ball, however, is considered a low-strength inflatable structure, much like all the other materials and inflatables that you see on Earth. What that means is it takes a low pressure to inflate this. And because of that low pressure, it has only one layer of material on it. This layer of material is both a gas barrier and a structural layer. Because it has a low pressure, it doesn't need a very high structural layer. But we all know from experience that these things are very fragile. They tend to break, they tend to pop, they tend to rip, and they're very dangerous. So if I say that I'm going to take this and I'm going to put it into space and I want you to live inside of it, you're probably not going to want to do it. But our space structures, our space balloons, if you will, are not like this. Okay? We have numerous layers of protection on the outside of our balloons that make them virtually bulletproof. One of the other advantages of our space structures, just like this balloon, is that it can be compressed and compact. It can be fit into a small launch shroud, launched into space, and inflated to over 200% of its initial volume. Additionally, when we launch an inflatable structure, for the same cost that we can launch a metallic structure, we can get over 3 times the volume. That's the same price to launch a vehicle. Instead of a metallic structure, you can launch an inflatable and get 3 times the volume. And I want you to visualize this, because this is very important. So I have some friends in the second and third rows. If you guys can come up right now. We're going to do a little demonstration. I need 6 of you, so Ron and Doug, if you can come as well. Kelly? Yeah. So there's these marks on the ground. Mm-hmm. Everyone just stand on one of them. There should be 6 of them. There's one way over there, and there's one way back there. Kelly, you can do that one at the front. So what I've done here is I have 6 people, and I divided them up into 3 different crews. They're all going to Mars. Okay? The first crew over here on the left, they're standing in a triangle. Can you stand on this triangle?
That's me.
That's you. So the first crew here on the left, standing in this triangle. The space in between these 3 people represents the volume of a typical capsule design, something you've probably seen before. It's going to take us to Mars or take us to the moon. And this is the habitable volume that they have to work with on their journey to Mars. Now, this triangle over here, and these 3 crew members are also going to Mars, but they are living in an inflatable structure. This inflatable structure has, what you see here is just 3 times the volume, but it can be a lot more depending on the design. So you can see here, pretty obviously, which vehicle would you rather take to Mars? This one, you're right. All right, you guys can sit back down. Thank you. So you're probably wondering, like, what's the catch? Why haven't we done this before? This looks awesome, it's amazing. Let's throw a bunch of money at it and let's build an inflatable structure. But one of the big problems with inflatables is that a lot of people are afraid of them. As I mentioned before, you put a balloon in space, it sounds scary. I talk to a lot of kids about this, and I tell them that we're going to put balloons in space. And they get a lot of concerned faces because of the same reasons. They know that balloons pop. I know that. You know that. But the balloons that we have on Earth are not the same types of balloons that we're putting in space. For example, this balloon, like I said, has a single gas barrier. We have a gas barrier on our inflatables as well, except our gas barrier is resilient to cold temperatures. It can be flexed multiple times without breaking. We also have redundant barriers, and it could be made of self-healing materials. So if there is a pinhole break or a leak, it can heal itself. Now, outside of that gas barrier, there's also a main structural layer, because our inflatables are high-strength inflatables. They have a high pressure on the inside, thanks to the vacuum of space that's on the outside. So we have a big structural layer that's made of the same material that you make bulletproof vest out of. It is bulletproof, and it's strong, and it's very stiff. And those are the main two layers, structural layer, the gas barrier. But outside of that, we have a space environment that's very dangerous and very scary. And so we have a shell on the outside of those layers that protects us from that space environment. For example, that shell has atomic oxygen protection, it's got thermal insulation, and it has multiple layers of micrometeorite orbital debris protection, or MMOD. MMOD is probably the biggest, or the scariest thing with inflatables. But the MMOD shield that we've created for our inflatable has outperformed the ISS MMOD shields in hypervelocity impact testing. So our inflatable balloon is actually better prepared for MMOD impacts than the current ISS metallic shields. So one of the other beauties of this structure and of inflatable structures is that they can be formed into a variety of different shapes. They can be used as a long-term transit vehicle to Mars. They can be used as a surface habitat on the moon or on Mars. This isn't the first time that we've thought about this. NASA first investigated inflatable structures back in 1961, 8 years before we went to the moon. In fact, the first ever EVA was performed by the Russians, and it used an inflatable airlock. This picture is from 1989. It was a design concept for an inflatable lunar habitat. And most recently, back in the late 90s, was a big project here at JSC called TransHab. Most of you have probably heard of it. TransHab was essentially the birth of today's design for inflatable structures. They invented a lot of new technology, mainly because they finally had the materials required to build these high-strength inflatables. One TransHab module was designed to fit in the payload bay of the space shuttle. It was intended to be berthed to the International Space Station, and it will provide 1,500 square feet of livable space in one module. That's about half the livable space of the entire space station. Now, after TransHab, the technology was taken and used by NASA to advance. It was also used by Bigelow Aerospace to work on inflatable structures. And this year, 2015, we will put the first inflatable module on the ISS. This new module, known as BEAM, will be a significant demonstration and advocacy towards the future use of inflatable structures. It will be the beginning of a new generation of space structures. So besides those uses, there are also a number of other potential applications for inflatables. I hope you've got your mind thinking a little bit. We can have this very large, very strong structure, and it can be compressed. You could fit something in a suitcase and then open it up and have a large volume. There's a lot of potential applications. Some of those applications are used in space. Some of them are being used now for new technologies. And there are even more applications that can be used on Earth. Some of the space applications you may have heard of is like a deployable solar sail, a deployable antenna, a hypersonic decelerator that's also deployable. And I know you've heard of spacesuits. Spacesuit is a life-saving example of an inflatable structure. It's a fabric structure that takes its shape when it's pressurized. It's the definition of an inflatable. There's also a lot of applications on Earth for inflatables. So inflatables could be used, for example, as a fuel collection device or storage device to prevent or to clean up an oil spill offshore. They could be used as an emergency hyperbaric chamber. If you were a deep sea diver and you were on a ship, and you did a dive, you came up too fast, and you need a hyperbaric chamber, and you're far away from any medical attention. The ship doesn't have a hyperbaric chamber, but we have an inflatable one. It's been compacted into a bag, and now we can inflate it, open it up, and it can be used to save your life. This technology can also be used under extreme conditions in extreme environments. It could be used as a safety shelter in Antarctica. It could potentially be used as a shelter for firemen who are caught in a wildfire. It could also be used as a quick deployed shelter during a natural disaster. In fact, during Hurricane Sandy a few years ago, most of the New York City subway tunnels became flooded with water. This was a big problem for the city. And since then, the inflatable technology, the same type of structural layer, gas barrier that we use, that we've designed, has been used and commercialized to build what's called a tunnel plug for the New York City subway system. These devices, like I said, is a big mass of fabric. It's packed up into a nice, pretty package, and then when needed, it can be deployed, fill up, and plug a subway tunnel. This is an excellent commercialization use of inflatable technology. And these are just a few things that I know about. I'm hoping that you guys can think about some more and think about some future potential applications that we can use for inflatables. They truly can be a life-saving technology. So, as I close today, this was a very brief overview, but I hope it got you thinking. And I want to reiterate the point that this is very important. You know, we want to explore. I want my kids to see Mars one day. And we can't get to Mars with metallic structures. We need to get out of our comfort zone. We need inflatables. Thank you.